Assalamu alaikum, guys. My name is Rasoul Turko, and today we're going to be talking about bilirubin metabolism too. So this lecture is inshallah going to be an easy lecture to go through. It's basically just one cycle of heme degradation, and then it's going to talk about jaundice. We're going to talk about jaundice and different kinds of jaundice and what happens in our body, what gets elevated, what's deficient, and what symptoms and signs do we get in patients. Okay, so when we talk about bilirubin, we're talking about, again, heme degradation. Okay, so we're talking about the breakdown of heme in our body and how we get rid of it. So what's important to know is what the heme structure is. Okay, so the heme structure is basically present in red blood cells mostly. It's going to be a structure where it's carbons and hydrogens around, while there's a Fe or an iron in the middle, and that is the structure of heme. So it's present in mostly hemoglobin and myoglobin. Myoglobin being the muscle cells, and or cytochromes, but mainly hemoglobin and myoglobin. Okay. So when we talk about heme degradation, again, we said that mostly all the heme that we have in our body is mostly in the red blood cells. Okay, so when the heme degradation process happens, we're talking about we have to talk about the red blood cell life, which is 3 months. So every 3 months, this heme degradation happens, and we get our beloved bilirubin. So where is it degraded? It's degraded in the macrophages. And in the macrophages, it'll break down in the macrophages, and then it'll go into the liver, and then continue its breakdown. But when we talk about macrophages, we're talking about two spots, two locations: bone marrow and spleen. Okay, so if an exam we get asked, where does heme degradation happen mostly? It happens in the bone marrow or the spleen. That's where it initially happens, and then after it gets broken down, it goes to the liver, and then gets further breakdown there. Okay. Again, as I know we said here, so most of the heme degradation that we have in our body is from red blood cells. The rest is from cytochromes. But for this exam for heme, again, what's important to know is that we get heme degradation, or the bilirubin, we get all of that from mainly RBC. And where does it happen? It happens in the phagocyte system, or macrophage, in other words, in the bone marrow and the spleen. Okay. All right. So now we're talking about compounds. We're talking about the different substrates that we get. So the Dr. Hannah, talked about two compounds. So a compound ending in ogen and compounds ending in N. Okay. So when we hear something that ends with the ogen, it basically tells you that this is a colorless substance. When we talk about something that ends with the N, we're talking about something that gets oxidized to form a conjugated compound. Okay. So conjugated compounds are oxidized, they end with the N, and they are colored. And then colorless are ogen suffix. Okay. So she put a couple of different examples here in structures that end with N, which are biliverdin, urobilin, and stercobilin. These stuff we're going to talk about in the later slides, but what's important to know for now is that biliverdin gets broken down into this green colored compound. Urobilin is the yellow colored, which is basically in our urine, which gives our urine the yellow color, and then stercobilin is what gives our feces the brown color. Okay. All right. Now, for this is basically the most important slide in the lecture. If you guys just memorize this, you're basically done with like 75% of the lecture. And then after that, you just have to memorize the names and what happens in disease. But this is what's important in the lecture. Okay. So as we said, heme degradation happens mostly in the macrophages of the bone marrow and the spleen. So here we start with the macrophage. We have first heme, which is what we said, the structure of iron with carbons and hydrogen around. So we have heme. It goes through heme oxygenase, and this is important to know. This enzyme is important to know. So it goes through heme oxygenase Through heme oxygenase, it gives you biliverdin. And biliverdin is what we said is one of those compounds that is green in color. And again, has NIN, that means it's colored, okay? So what's important about this enzyme is that this enzyme yields Fe2 and CO, carbon monoxide. This is one of the only reactions in our body that we know of so far that gives you carbon monoxide. Okay, so this one gives you Fe2 and carbon monoxide, and it uses NADPH. The doctor didn't really stress on this part here, but she stressed on the part that it gives you it's heme oxygenase, that's the enzyme, and that it gives you Fe and carbon monoxide. Okay, so from biliverdin, we use biliverdin reductase to get what is called bilirubin. Okay, this is our first bilirubin. Now this bilirubin is the unconjugated form of bilirubin. Okay, so this is unconjugated. Okay, it's unconjugated or indirect. It's indirect or unconjugated. This is the first form of bilirubin that we have. Okay, so this bilirubin is indirect and conjugated. Okay, and this is all happening again in the bone marrow or in the spleen of the macrophage. Okay, after that, this unconjugated bilirubin is toxic in our body. Okay, and because it's toxic, it has to bind to something that would make it less toxic or make it be able to be transported away from the macrophage. Okay, so here it binds to albumin. So when it binds to albumin, it can get transported to where it needs to be transported in the blood to the liver. Okay, so albumin first of all makes it less toxic because bilirubin on itself, unconjugated bilirubin, is toxic. So when it binds to albumin, it makes it less toxic and it makes it able to be transported in the blood. It needs to be furtherly degraded in the liver. Okay. When it's in the liver, it gets through bilirubin UDP glucuronidase transferase to give you bilirubin diglucuronide. Okay, and through this reaction, it uses 2 UDP glucuronic acid to give you to give you the final product. So it uses bilirubin UDP glucuronidase transferase, and it uses 2 glucuronic acids. Okay, you notice how this is a 2 UDP glucuronic acid, and then after the reaction happened, the glucuronic acids are gone. Okay, so it uses 2 glucuronic acids using this enzyme bilirubin UDP glucuronidase transferase. Now this product here is the conjugated form of bilirubin, aka the direct form of bilirubin. Now after that, it gets to the bile, and then small intestine. And small intestine, it gets metabolized either it goes to the urine, it goes to the kidneys, and gets excreted as urine, or it gets from the small intestine, it goes and becomes feces, basically. Okay, and this is the whole process. Okay, so here we see the so what we mean by heme, for example. So when someone gets injured, so when someone hits a table, for example, the heme degradation is happening where it doesn't usually happen. So you know how we said it happened in Spain or the bone marrow. When you hit something, you are killing those red blood cells, and they're dying in that spot exactly. Which is why you see the different color. We see first green, then we see red, and then it turns into a little purple. This is basically just telling you that this is where degradation happens when you hit parts of your body, instead of it happening where it needs to be happening in the macrophages in the liver. Okay, I'm going to go over this one more time because this I think it's pretty simple, and I want to get it across right away, so we can just so you guys can just go over it once and you'll be done with it, because it's pretty straightforward. Okay, so first of all, we have heme. We are in the spleen. Again, we are in the spleen or in the bone marrow. Okay, we are in the spleen or in the bone marrow. So we have heme. It goes through heme oxygenase, the only reaction that produces carbon monoxide. It gives you biliverdin. Biliverdin is the green compound again, okay? From biliverdin, it goes to biliverdin reductase. So it's pretty easy to remember. So first of all, heme oxygenase happens, and then biliverdin reductase. So you'll get the name of the enzyme from the substrate, okay? Biliverdin reductase gives you bilirubin. This is the unconjugated indirect bilirubin. From bilirubin, then it binds to albumin, which takes it to the liver. In the liver, it goes from bilirubin to bilirubin diglucuronide through this reaction using 2-glucuronic acid, okay? And then when it becomes this is when it becomes the direct or the conjugated bilirubin, okay? All right. Okay, again, I'm going to go over it again in specific reactions. So biliverdin, again, it produces carbon monoxide and Fe2. Okay, it's the only reaction that produces CO. And what's important here to know is that when we want to test the activity of heme oxygenase in a person, and heme oxygenase again is this enzyme. When we want to test this heme oxygenase enzyme, like we're making sure that the heme is being degraded smoothly in a person. We check for their carbon monoxide content of the expired air in the lungs. Okay, so this is just a quite quick side note, but just to really emphasize the fact that carbon monoxide gets produced from heme oxygenase during the first reaction of heme degradation of bilirubin metabolism. Okay, right. Now for the yellow bilirubin, so basically it just says that biliverdin is reduced to form yellow-orange bilirubin. And then this bilirubin here, this guy here, is the bilirubin that's unconjugated and indirect. Okay. So from biliverdin, it goes through biliverdin reductase to form bilirubin, and that bilirubin is the unconjugated bilirubin. And this will be important later when we talk about different diseases. Okay. And this is just a quick side note that bilirubin are called bile pigments. Why? Because after they go through the liver, they go through the bile and then into the small intestine. So they're called bile pigments or bile derivatives. Okay. All right. Albumin. So albumin is what makes bilirubin basically less toxic because it's usually toxic. The unconjugated bilirubin is usually toxic. So when it binds to albumin, it's not unconjugated anymore. It's not unconjugated bilirubin anymore. So it is still unconjugated, but it's bound to something else, bound to albumin. It's not freely in our body. It's bound to something. It's still unconjugated. It's just bound to something. It's not just freely floating, right? So when it binds to albumin, it helps it gets transported from in the blood through to the liver. Okay. So now the conjugation. So we said here after the unconjugated bilirubin goes to the liver. In the liver, it goes through this enzyme, bilirubin glucuronidase transferase, or bilirubin UGT, and through it transfers two glucuronic acids from UDP to bilirubin. Okay, and this bilirubin here, diglucuronide, is the one that is conjugated or direct. Okay, it's pretty easy to remember that this is the conjugated one because we said that the last reaction gives two glucuronic acids, and this one here is diglucuronic acid, right? So this is the one that's conjugated. Okay, so after the conjugated bilirubin is in the liver, and after it's become the conjugated form, it gets transformed into the bile, and then in the bile, again, it gives you two things or one or two things. Mostly, it goes through, it gets reduced by the gut bacteria to give you urobilinogen, okay? So again, it goes through from the bile, goes into the small intestine. In the small intestine, it gives you urobilinogen. This urobilinogen, again, it's ocean, so it's colorless. Now, from urobilinogen, it goes through different pathways, either this or this, okay? So it either goes to becomes stercobilin or urobilin. So if it becomes stercobilin, that means it's going to stay in the small intestine and it's going to get oxidized by bacteria, and then it's going to get excreted, and that's what we know as that's what gives our feces the color brown. Okay. Or if it gets transported to the kidney, if it doesn't stay in the small intestine like here, if it gets transported to the kidney, it becomes urobilin. And this urobilin is what gives our urine the yellow color. Okay. But mostly, again, if you look at the different like amounts we get, it's 250 a day we get from circobilin, while here we only get one. So you see that mostly it gets oxidized in the small intestine by the bacteria from circobilin, and this urobilin doesn't happen as much as circobilin does. Okay, so what's important here to know is that here we go from conjugated bilirubin to urobilinogen, and this is what's important to know. After urobilinogen is when we go to either circobilin or urobilin. Okay, all right. Now toxicity. So why is bilirubin toxic? Uh why is it bad for our body? Why do we need to get it excreted? Is because it inhibits DNA synthesis. Okay. It's a couple of oxidative phosphorylation, so it messes up with our glucose metabolism, and it inhibits ATPs. So ATPase activity, it's those plasma plasma members that we talk plasma transport, sorry, that you guys talk about in every block. And these are very, very important. So when it messes up with those transports, it messes up with the interstitial pressure in our cells. Okay. So it just inhibits DNA synthesis, oxidative phosphorylation, and ATPase activity. Okay. Now, okay, so we finished the actual degradation of bilirubin. It's pretty straightforward. We only need to know like two and three enzymes. Now we talk about what goes wrong, okay, and what can go wrong and how it can go wrong, okay. So there's jaundice. So jaundice is the yellow color of the skin, nails, and sclera. Sclera meaning the whites of the eye. It's caused by increased bilirubin levels. Okay, when we have increased bilirubin, this is when you get jaundice, or in other words, called hyperbilirubinemia. Okay, and when does that happen? If you think about it, when do we get increased bilirubin levels? We get increased bilirubin levels when the enzymes that give you those bilirubin, whether it was unconjugated or conjugated, they are deficient. We don't have those enzymes, and therefore we're getting increased bilirubin levels, and we're not being able to excrete them. We're not being able to get it from, let's say, unconjugated to conjugated. So it's stuck here. We have high number of bilirubin. Therefore, we can't make it down to become urobilin or circobilin to be excreted, right? We have high levels, or we have high levels of it's getting from unconjugated to conjugated, but from conjugated, it's not becoming urobilinogen, for example, and therefore we can excrete it. So it's high levels of those bilirubin, whether conjugated or unconjugated, due to the deficiency in enzyme that break them down. So jaundice is seen at 2 to 3 milligrams, while the normal is only 1. So when it's 2 or 3, that's when we see jaundice. We start seeing yellow tips of the fingers, yellow around the sclera, or yellow skin usually as well. Or yellow skin usually in severe jaundice, but yeah, it happens in hyperbilirubinemia. Okay, so at very, very high levels, bilirubin actually can cross blood-brain barrier and precipitate in the basal ganglia. And in the basal ganglia, it gives you irreversible brain damage, and it's called kernicterus. So kernicterus is a form of jaundice it's not a form of jaundice. It's a symptom of jaundice that happens when there's irreversible brain damage to the basal ganglia. All right. So this is the different kinds of hyperbilirubinemia or jaundice. So we get it in something called prehepatic or hemolytic jaundice, obstructive, hepatocellular, and neonatal. Okay. The difference is, so let's go one by one. So hemolytic or prehepatic jaundice. So we get deficiency at different parts of the cycle. So when we're talking about prehepatic, we're talking about deficiency in the enzyme and bilirubin before it even gets to the liver. So deficiency in it becoming unconjugated. We don't worry about the conjugated part because the conjugated part has already happened in the liver. We're talking about the part where it's unconjugated, which happens in the bone marrow or the spleen. So here we see that there's deficiency in which we have increased bilirubin. We have very increased bilirubin. How does that happen? It happens when there's production of bilirubin faster than it can get conjugated. So we have increased production of bilirubin here, and it's getting produced more than we can get it excreted. So we have so here there is no deficiency in the enzymes. It's just getting produced more than we are capable of working with, and therefore there's high bilirubin. It's still, some of it is still getting conjugated in the liver here, and the intestine here, but it's being produced at a faster rate, and this is why we have high bilirubin in prehepatic jaundice. In post-hepatic jaundice or obstructive jaundice, there's an obstruction here after it has already become conjugated. So here this is already conjugated, and there is probably an obstruction here that we're going to talk about here later. And this obstruction is not allowing us to go through it through the cycle, and we have increase in bilirubin glucuronide or diglucuronide, which is the exact same thing, which means we have an increase in conjugated bilirubin, and you can see it here. So we have elevated levels of conjugated bilirubin, which is called conjugated hyperbilirubinemia, and this results from the presence of different things. And I think those stuff are going to be important because I think in the exam they might bring you like a case scenario, and they tell you, for example, there is someone comes in with like symptoms of jaundice, and they tell you it's due to an obstruction in the common bile duct, for example. And what's the reason for here? And the reason for obstruction in the common bile duct. So notice how all these stuff. So like presence of tumor or having bile stone or having obstruction of common bile duct. This is happening post spleen and bone marrow. So it's happening after this has already gone unconjugated and then has gone conjugated as well. So it's happening after it goes through the liver. That means there's a problem here in the conjugated bilirubin. So its presence in tumor, bile stones, obstruction of the common bile duct, which prevents passage of conjugated bilirubin into the intestine. So we have high CB or high conjugated bilirubin. Stools are pale or clay in color. Why is that? Why does that happen? Because again, we're not being able to break down CB into urobilinogen and then into stercobilin, which gives the feces its color. So here we're not getting brown in our feces. CB regurgitates into the blood. So again, because there's a lot of CB, it ends up in our blood. It ends up getting back into our blood because there is no place for it to stay in the liver or between the liver and the obstruction that there is. So it goes back into the blood, and it ends up being in our blood. So we have just pre-conjugated bilirubin in our blood. So patients here, they experience GI pain and nausea, and eventually it's excreted in urine. CB is excreted in urine, which darkens over time. So over time, because we are not being able to secrete this, excrete this in our feces, it's going into our urine, which is getting darker, and that is referred to urinary bilirubin. So urinary bilirubin, when our urine is getting dark, it's due to conjugated bilirubin or post-hepatic or obstructive jaundice. Okay. All right. So now hepatic jaundice. So this is hepatic jaundice here. So hepatic jaundice basically happens due to liver disease, okay? So that means if it's due to liver disease, that means there is no problem up there. There is no problem in the unconjugated part here, and there's no problem in making the conjugated part of it. So this is why we still have high bilirubin and high bilirubin glucuronide, but we're not being able to again continue our cycle. So especially in hepatic jaundice, especially we have increase in both bilirubin and bilirubin glucuronide. Okay, and this is right here. The doctor didn't really say anything about it. She only mentioned this is parts of the disease. So hepatitis, liver disease, and liver cirrhosis. But I think it's important to know that in hepatic jaundice, there's increase in bilirubin and bilirubin glucuronide, or in other words, there's increase in direct and indirect uh, bilirubin, or there's increase in unconjugated bilirubin or conjugated bilirubin. Okay. Okay. Now in the neonatal jaundice. So neonatal jaundice is basically the process is stopped at unconjugated bilirubin. So there's a problem here, which gives us an increase in bilirubin, and that's why we can't continue and give you conjugated bilirubin in the liver. And how does that happen? So first, what we need to know first of all is actually a lot of newborns do actually get a rise of unconjugated bilirubin. So they get that increase in the first week, and that is normal because of it's called transient physiological jaundice. That is because their UGT, which we said is the enzyme that gives you conjugated bilirubin, uh, is low at birth. So it usually becomes normal at 4 weeks. I think the shadow percentage of 80%. So 80% of newborn infants do go through that, and that is called physiological jaundice. It's due to this enzyme UGT, which gives you the conjugated bilirubin, and it can become serious by causing encephalopathy or can kernicterus, and that's when it becomes pathological jaundice. How do we treat it? We treat it by blue fluorescent light. Okay, so we put the baby under a blue fluorescent light, and this fluorescent light converts the unconjugated bilirubin into a more soluble isomer, which can get excreted without being conjugated. So basically, we're skipping this little step of UGT because here we can excrete it without getting it conjugated by UGT. Okay. So under neonatal jaundice, we also talk about genetic UGT deficiency. Okay, and when bilirubin, when we're talking about UGT deficiency, we're talking about when there's low conjugation of bilirubin due to a deficiency in the genes, and we get increased unconjugated bilirubin in the body. We get unconjugated due to a deficiency in UGT, and that is due to again a genetic deficiency in UGT. We get high unconjugated bilirubin. There's two examples. There's Crigler-Najjar, which is severe, and there's something called Gilbert syndrome, which is a mild condition of genetic deficiency. So what are they? So in I think I'm gonna go over this picture. Yeah. So let's go over the process again. So first of all, we get our red blood cells, which have a life of 120 days or 3 months. Those blood cells obviously produce a bilirubin in the bloodstream. So this unconjugated bilirubin, this bilirubin that was produced in the blood and from the blood cells, which happens in the bone marrow or the spleen, then goes to the liver. This in the liver, when it gets transferred to the liver, when we have a Crigler-Najjar syndrome, we have low activity of UGT. UGT is not working. And when UGT is reduced or absent, bilirubin is unable to be effectively conjugated. So we don't get conjugation of bilirubin. Hence, we get increase in unconjugated bilirubin. So it's not getting conjugated. It's not going through the cycle. So right away we have increased unconjugated. And this unconjugated bilirubin cannot be secreted into the bile for elimination. And then this level increases the glycerin. Yeah. So first of all, we have no UGT, no or low UGT. This ends up giving us high unconjugated bilirubin. And because there's high conjugated bilirubin now, it either regurgitates the blood or it goes into, or it can become worse and go into the brain and become connectors. And that's basically what we're saying here. So UDP glucuronyl transferase is absent. It's either absent or low, but mostly in curricular Najjar, it's basically the severe form of it. And this is what they're going to tell you in the exam. In the exam, they're going to give you the severe form. So they're going to tell you this is absent or it's low. It's going to be increased unconjugated bilirubin, as we said. But remember how I said in jaundice, it's usually 2 to 3 milligrams. Here in curricular Najjar, we're talking about 20 to 50, which is a huge number compared to normal jaundice. Huge, which is why it's so severe. So we get excessive persistent neonatal jaundice. Kernicterus, again, we said which is irreversible brain damage. It can happen. And the only curative form of this disease is liver transplantation. So we have to give them a whole new liver, because obviously the liver they have, the deficiency in the enzyme is so severe that they need to change the whole liver. Okay, because the enzyme that which is UGT, which is responsible for bilirubin metabolism, is not working. So without treatment, Najjar syndrome is not compatible with life. So it's a very serious disease. Okay. Now, last thing we're going to talk about is the Gilbert syndrome. And Gilbert syndrome is basically the same idea of curricular Najjar, except it's not severe. It comes in mild jaundice. Okay. So what's affected here? Again, it happens in adolescents. It doesn't happen there. We talk in curricular Najjar. We talk about neonatal. Here it's adolescents. So again, it's mutation in the promoter gene, UGT1A1 gene. They're really specific about Gilbert. They found the gene that is responsible, but it's responsible for the exact same enzyme that we talked about. So both Gilbert and Crigler, they have deficiency in the same enzyme. In Crigler, it's very low or absent. Here, it's a mild reduction of the enzyme. The rest results again in the elevated indirect bilirubin, indirect or unconjugated bilirubin. Patients present with no symptoms or unspecific symptoms such as like fatigue. But mostly what's very important to know is that in Gilbert syndrome, it's always mild. It's always mild jaundice compared to curricular Najjar. So it's transient, usually mild jaundice, varying from mild scleral jaundice to general jaundice. Treatment is not required because it's benign. And it might have some triggering factors such as stress or fasting periods. Okay. I want to like reiterate a point here is that the difference between those different types of hyperbilirubinemia. So when we're talking about prehepatic, we're talking about the increased production of unconjugated bilirubin while the cycle is still going. So the cycle, we're still being able to conjugate the bilirubin and excrete it, but we just have an increase in unconjugated bilirubin. So the production is increased compared to how often we excrete the bilirubin. Okay, obstructive or posthepatic, so after the liver. What's high yield here? What do you need to know here is that this is due to an obstruction. So it's a tumor, obstruction of common bile duct, and that will increase our conjugated bilirubin. So that yields an increase in conjugated bilirubin. So here we talked about an increase in unconjugated. Here we're talking about an increase in conjugated bilirubin. So for hepatic jaundice, we talk about increase in bilirubin It's unconjugated and conjugated bilirubin. So we talk about both here. In neonatal jaundice, it's most likely, or like for the sake of this lecture, it's always going to be increase in unconjugated bilirubin. So when we talk about Krigler-Najjar or Gilbert, we're talking about increase in unconjugated due to the deficiency in UDP in the enzyme here. In the enzyme here. So here we're talking about here and here we're talking about increase in unconjugated. Here we're talking about here's the only place we talk about increase conjugated. Here we talk about both unconjugated and conjugated. Okay. So I understand this is online, so we're not going to be able to go over some questions. I just found 2 questions. I'm going to try to go over them to give you guys a better understanding of how to solve those questions. Because inshallah there'll be easy questions, and they won't bring a lot from this lecture in HLS, but it's good to get those questions basically secured. It's good to know that you have those questions secured in advance. So here a 9 months old infant. So here right away we're probably going to be talking about a case of Kruger or Gilbert, okay? Because we're talking about a neonate here, or basically we're talking about an infant here. So suffered bouts of jaundice and was diagnosed with severe. So severe is important here. Severe icterus, again jaundice, shortly after birth. Has that occurred okay? During the period of jaundice, serum analysis showed an increased concentration of indirect bilirubin with no detection of direct bilirubin. Okay, so this same is not important. What's important here is that we have increased concentration of indirect bilirubin right away. Severe icterus, and we have and this person has died of current icterus. So this is very, very severe. The premature death and early findings suggest which of the following. Again, we're talking about a very, very severe. We're talking about a really severe syndrome here. So we're going to talk about here. It's going to be either Kruger or Gilbert here because we're going to talk about 9 months old. So it's a very severe. So it's going to be Kruger. Why is it not G6PD? So again, G6PD. Did I mention it here? Yeah, I forgot to mention it. So yeah, this is G6PD. So G6PD in prehepatic, that's the first one here. In this one it can happen in sickle cell anemia, pyruvate kinase, or eating fava beans while having G6PD deficiency. Okay, and the doctors mentioned eating fava beans. You guys took it in more how it's basically worsens the G6PD deficiency. And here it could be either this or this because it's so severe and the person has died of connectors. It's still definitely going to be Kruger-Najjar. Okay, so here I don't know it's showing this, but a 35-year-old male patient goes to the ER because he is troubled by his chronic fatigue and persistent abdominal discomfort. Additional signs in the patient are mildly ecteric sclera. So ecteric sclera, so here we have jaundice. The ER attending calls for a blood workup for bilirubin, okay? So this person is having jaundice already. And the physician suspects that the patient has Gilbert. So when they have Gilbert syndrome, which of the following enzymes would be expected to be found at reduced levels if this is the correct diagnosis. So which of the following enzymes, basically, this whole question is basically saying which of the following enzymes is deficient or has a problem in Gilbert syndrome. So it's a straightforward recall question here. And what we said, Gilbert syndrome has deficiency. A patient with Gilbert syndrome, what deficiency would they have? They would have deficiency in the enzyme that gives you conjugated bilirubin, which is UDP glucuronyl transferase. Okay, we talked about it over here. Yeah, so it's deficiency UDP glucuronyl cell transferase, and that happens again for Gilbert and for Krigler-Najjar, except this one here is severe. The other one is mild jaundice. Okay. And that's going to be all for me today. This is an easy lecture, inshallah. It won't be too hard to study. And inshallah they'll bring like straightforward questions because they can't like trick you with this lecture. If you guys have any questions, please let me know. I left my information right here. If you have any questions, let me know. Thank you very much and good luck to all of you.